The solar cell is the driving force of any PV system. It converts sunlight into usable electricity. Here, we will describe how a solar cell works. We will start by explaining the photovoltaic effect. We will then discuss semiconductors, which are the most commonly used materials for creating solar cells. Photovoltaics perform an energy conversion process. Specifically, they convert energy from light into electrical energy. Another way of saying this is that they take energy from photons and use that energy to drive an electrical current. The driving force is a voltage, so the process is called the photovoltaic effect. The photovoltaic effect takes place over 3 steps. We will show these steps in a very simple solar cell schematic. The first step is the generation of free charge carriers. Our device absorbs light, and through this absorption, free charge carriers are generated. The next step is the separation of charge carriers. In order to use these charge carriers, the positive and negative charge carriers must be separated to avoid the charge recombination. Finally, the charges must be collected at electrical contacts, which are usually metallic. With this collection, there is now a voltage difference between the 2 contacts of the solar cell. So we have successfully converted photon energy into a voltage. If a resistive load is connected between the 2 terminals of the solar cell, the current will be driven through the contact and perform electrical work. There are various different approaches and materials to achieve the photovoltaic effect. The most common solar cell device is made from crystalline silicon, a semiconductor. To understand how we achieve this effect using crystalline silicon, we have to explain how semiconductors work. We can use the energy band diagrams to explain semiconductors. These bands represent energy states of electrons in a material. The valence band represents the highest energy states of electrons in a material at absolute 0 temperature with no outside energy input. The conduction band represents energy states where the electrons are mobile and can flow. So for a material to be able to conduct electricity, we need electrons occupying the energy states in the conduction band. Before we look at semiconductors, let's take a look at band diagrams of conductors and insulators. A conductor has a band diagram where the valence and conduction bands overlap. This means that valence electrons are already at energy states where they can conduct electricity. The conductivity of a conductor is only limited by the friction that the charges experience, which is known as the resistance. An insulator, on the other hand, has a conduction band completely removed from the valence band. There's a very large gap between the valence band and the conduction band. There are no free charges available here and no reasonable mechanism to move electrons from the valence band up to the conduction band. Like insulators, semiconductors have a gap between the conduction and valence band, but the gap is much smaller. This smaller gap is called the band gap energy. We can control the amount of charge carriers in the conduction band by adding enough energy to our electrons to overcome this gap. We call this exciting an electron to the conduction band. When this happens, the electron is now mobile and can conduct through the material. A so-called hole is left behind. This represents the absence of an electron in a valence bond. Holes are also mobile in our material. When we excite an electron this way, we say we have generated an electron-hole pair. We refer to both electrons in the conduction band and holes in the valence band as free charge carriers. There are a number of ways to increase the density of free charge carriers in our material. We can inject electrical current in our material, or we can apply energy into it through heat, or, as in the case of solar cells, illuminating it with light. We can also manipulate the charge carrier concentration through a mechanism called doping. We will explore doping further in the next video. In this video, we discuss the working principle of a solar cell. This working principle is called the photovoltaic effect, which involves the generation, separation, and collection of free charge carriers. Then we discussed semiconductors, which are the most commonly used materials for making solar cells. In the next video, we will explore crystalline silicon specifically in more detail and discuss the p-n junction.